This is the second part of the 19th lesson in heat transfer. In the 19th lesson, we have been discussing tips and tricks for solving external flow convection heat transfer problems. In the first part of the lesson, we looked at the principle of superposition in heat transfer. In this second part of the lesson, we will discuss how to solve problems when the surface temperature is unknown. By the end of this lesson, you should be able to recognize that problems in which the surface temperature is unknown present an additional challenge. And you should be able to use a guess and check strategy to solve problems of this type in spreadsheet software or in MATLAB. On with the lesson. In some problems, we don't know what the temperature of the fluid-solid interface is. Consider the following example. In this example, electronic devices are mounted on a printed circuit board shown below. The board may be mounted in a personal computer or in a server operated by a company such as Microsoft. Cooling devices such as these is a common problem in heat transfer. To cool the devices, air at 27 degrees Celsius with a free stream velocity of 10 meters per second is passed over the thin electronic devices. Each device is 4 millimeters by 4 millimeters and dissipates 40 milliwatts of energy. This 40 milliwatts of energy represents the rate of thermal energy generation within the device. The thermal conductivity of the printed circuit board is small enough that conduction through the board can be neglected. All the dissipated energy is removed from the top surface of the device via convection heat transfer. The question is, what is the surface temperature of the fourth device, whose center is located 15 millimeters from the leading edge of the plate? We are also told that in this particular situation, a turbulator is present to promote early transition of the boundary layer, such that the boundary layer is approximately turbulent from the leading edge. This means that the boundary layer essentially has a very, very rapid transition to turbulence. Because the surface temperature is unknown, we cannot calculate the film temperature. It is also unknown. We thus do not know at what temperature to look up the properties of the air. This is the additional challenge associated with problems in which the surface temperature is unknown. We need to develop a strategy to tackle problems of this type. Our strategy is called iteration. In order to solve this problem, we must iterate towards the solution. To iterate means to make a guess, check to see if that guess is correct, and then update the guess until the guess matches the solution. While iteration can be done by hand with pencil and paper, and the number of iterations required to arrive at the solution usually does not exceed 3 or 4 for most external flow convection heat transfer problems, use of a computer spreadsheet can greatly assist the solution procedure. I will demonstrate a spreadsheet later in the video. Let's walk through the first iteration by hand together. Here is how the iterative procedure works. Step 1. Make a guess for the unknown surface temperature. This guess is arbitrary, but one develops an engineering sense of appropriate guesses after the solution of many problems. Let's guess 100 degrees Celsius in this case. With a guess for the surface temperature, we are in a position to calculate the film temperature. We do so and see that the film temperature is 63.5 degrees Celsius or 337 Kelvin. Now that we have a film temperature at which to look up fluid properties, we can do so. The properties for atmospheric air are listed in Table 8.4 on page 995 of your textbook. Because this temperature, 337 Kelvin, is not one of the rows directly in the table, we must linearly interpolate in order to arrive at the property values at this temperature. I have done the linear interpolation, and the result of the interpolation is as follows. The kinematic viscosity of the air at this temperature is 19.58 times 10 to the minus 6 meters squared per second. The thermal conductivity is 0.029 watt per meter Kelvin, and the Prandtl number is 0.702. The third step is to calculate the average convection heat transfer coefficient and then use it to calculate the surface temperature. We are interested in the heat transfer over the fourth device. There is a balance between the rate of electrical energy dissipation and the convection heat transfer out of the top of the device. This balance is what allows us to estimate the surface temperature of the device, but we require to know the total convection heat transfer rate, and thus we need the average heat transfer coefficient associated with the heat transfer over the top. We begin by calculating the Reynolds number associated with the flow at the leading edge and the trailing edge of the device at x1 and x2. Because the device is 15 millimeters on its center and is 4 millimeters on a side, the leading edge is 2 millimeters in front of the center, and the trailing edge is 2 millimeters behind the center. We calculate values of the Reynolds number 6,640 and 8,684. These values are less than 500,000, and the boundary layer would have been laminar had there not been a turbulence promoter in this particular problem, causing the boundary layer to transition to turbulence before the fourth device. We need to look up an appropriate Nusselt number correlation. The mixed boundary layer correlation can work in this particular case. If the boundary layer transitions to turbulence early, close to the leading edge, the mixed boundary layer correlation can be used so long as the parameter 871 is set to 0. We now can calculate the average Nusselt number at the leading edge and the trailing edge, anticipating using the principle of superposition. Here the values are calculated. 0.037 times 6,640 raised to the 4/5 times a Prandtl number raised to the 1/3 yields 37.6. Similar calculation at the trailing edge leads 46.55. We now use the definition of the Nusselt number to calculate the average heat transfer coefficients at the leading and trailing edge. Remember, these represent the average heat transfer from the leading edge all the way to x1 and x2. From the principle of superposition, which was covered in Part A of this lesson, we can calculate the average heat transfer coefficient associated with the heat transfer over the fourth device. Review the Part A lesson if you are not familiar with this equation. The average heat transfer coefficient is 169.1 watt per square meter Kelvin. We now use the energy balance from an analysis of the control volume of the fourth device, which says that the rate of thermal energy generation must equal the rate at which that energy is removed by convection heat transfer. And we have substituted Newton's law of cooling, the appropriate form, using the average heat transfer coefficient in order to quantify the rate of heat transfer off the top surface of the fourth device. Solving this equation for the unknown surface temperature and substituting values yields a surface temperature of 41.8 degrees Celsius. The fourth step of the iterative procedure is to compare the calculated surface temperature and the guessed surface temperature. The guess was 100 degrees Celsius, and the calculation yielded 41.8 degrees Celsius, and air of 58.2 degrees Celsius. The air is larger than the value of the surface temperature. We thus need to iterate again. Go back to step 1 and continue this procedure until the air is smaller. The use of spreadsheet software assists in the calculations. Here is the result after one iteration. We have already stepped through calculating each of these values. The film temperature based off of the guessed surface temperature. We looked up the fluid properties at the film temperature based on the guess. Then we calculated a new surface temperature by first calculating the Reynolds numbers at the leading and trailing edges, the Nusselt number, using the appropriate correlation for the Nusselt number, the average heat transfer coefficients at the leading and trailing edges. We used the principle of superposition in order to calculate the appropriate average heat transfer coefficient for the fourth device, and then we calculated the new surface temperature and the air. We now continue this procedure by setting the new guess equal to the last result. So here, the new guess becomes 41.8 degrees Celsius. We calculate a new film temperature. We look up and enter new property values. And then we can simply copy and paste these calculations once the new property values have been entered. I will now walk through that process here. Here, the new film temperature is calculated. It is lower, 308 Kelvin. New property values are looked up for the air at this new film temperature. Finally, a new surface temperature is calculated. Here is the result after a second iteration. The new surface temperature is 41.5 degrees C. This is much closer to our guess of 41.8 degrees Celsius. The air is now only 0.3 degrees Celsius. One might conclude that this is good enough. If we were to do one additional iteration, the guess temperature and the calculated temperature agree within 3 digits, and we would say to the 10th of a degree C that there is no air. The surface temperature is thus 41.5 degrees Celsius. This is how one uses iteration to solve for an unknown surface temperature. This is the end of the 19th lesson.